Welcome, dear civil engineering people. So now we are going to solve a simple problem of a frame using portal frame methodology. Here we go. This portal frame method could be used only for low-rise buildings. You cannot use for high-rise buildings, and it is also unsuitable for building frames having different number of bays at different floors. So uniformity should be maintained. If this is missed out, you cannot use this portal frame methodology. Now the assumptions are point of contra-flexure is located at the mid-height of each column, and a point of contra-flexure is located at the center of each beam. The horizontal shear is divided among all the columns on the basis that each interior column takes twice the shear carried by the exterior column. So we proceed further for a portal frame method. So here you can see that the loads 40 kN and 24 kN are acting, and the frame is having joints A, B, C, D, E, F and G, H, I. You can see that the span is between A and B is 4 meter, and between the point B and C is 8 meter, and the height of FC is said to be the 2.5 meter, and here IF you have 5 meters. Now we are locating the point of contra-flexure for the top portion. Now you take the shear as P, and the shear acting at the point NB 2P, and the shear at the point OB P. Now this is the assumption that point of contra-flexure is exactly at the center, that is 5 meter divided by 2, that is 2.5 meters. Then also you have got here the twice the shear is acting at the mid column, that is the middle one between the other two columns. So other two columns have the shear P, and the center column is sharing twice the shear as that of the exterior columns. So this interior column is sharing the twice the shear of the exterior columns. From this concept we get to know that the value of P is around 10 kN. Yeah, here it goes 10 kN. Now we locate the point of contra-flexure for the lower portion, and here you can see that this is the point of contra-flexure. It's mentioned here. Now you cut the frame at this location, and you take the shear at the exterior column as P and the interior column as 2P. So here you can see that 40 plus 24, that is equal to 64 kN, and that is equivalent to 4 times the shear. So when you divide 64 by 4, you are ending up with P is equal to 16 kN. Now we have found out the shear for the exterior columns as well as the interior columns. Now you can see that I would like to point out one thing, that always when you solve the portal frame method, you take the convention such that the beam moments are clockwise. So you can see that the beam moments are clockwise like this, and always take the column moments as anti-clockwise. So these are the moments in the beams which have been represented. If you take the beam GH separately, for example, if you take the beam GH, you can see that the moment at the beam is just like this. For example, if you take the moment is mentioned as MGH, and here the moment is mentioned as MHG. Here you can see that both the moments are beam moments, and they are acting in the clockwise direction. If you take the column, for example, if you take the column GD, so if you take the column GD, you mention the moments like this. This is MGD, and this moment is MHG. dg. So this kind of sign convention will be adapted throughout the evaluation and solving the problem. Yeah. Here you can see that the moments marked in red color are the beam moments. So I have drawn the free body diagram and mentioned the moments in the beams using red color, that is clockwise, and also you can see that the blue color is the moment acting in the columns in anti-clockwise. All the moments in the beams are taken to be clockwise and all the moments acting in the columns are taken to be anti-clockwise. Now, yeah, the same thing is repeated here more elaborately. You can watch out here that the column moments are anti-clockwise and beam moments are clockwise. Now proceeding further, we are going to find out the column moments now. So this is the pictorial representation showing you the free body diagram mentioning the column moments and the beam moments as well as the shear in the columns are mentioned. We will be using this 10 kilonewton shear, 20 kilonewton, 10 kilonewton, 16 kilonewton and 32 kilonewton, 16 kilonewton for evaluating the column moments MGD, MDG, MHE, MEH and so on. Now let us take this portion GD. You can see the GD is the free body diagram. This is the free body diagram of the column GD, and here 10 kilonewton is the shear acting. Now if you want to find out the moment, you can see that this is 10 multiplied by the length of the column divided by 2, that is equal to 25 kilonewton. So this MGD is equal to MDG. Similarly for MHE, you take the column HE and 20 times multiplied by 5 divided by 2, which gives you 50 kilonewton meters. Similarly, you take the column here IF and DA. So for IF, you can see that the value of the moment is 10 multiplied by 5, that is the height of the column. The 10 is the shear divided by 2, which gives you 50 by 2 equal to 25 kilonewton meter. Similarly, if you take the column DA, MDA equal to MJD. All the column moments are acting in the anti-clockwise direction. So from this you can evaluate 16 times 2.5 divided by 2, that is equal to 20 kilonewton meter. And similarly, you take the column BE and take the column CF. So you can evaluate using the shear 32 times 2.5 divided by 2, and here 16 times 2.5 divided by 2. So you are getting the values of all the column moments have been evaluated. So you can see that the column moments have been evaluated and represented here as 25, 25, 50, 50, 25, 25, 20, 20, 40 and 40, 20, 40. Now how to evaluate the beam moments in the next step? You take the joint G. This column moment should be balanced by the beam moment acting in the clockwise direction. So MGH should be definitely 25 and MHG is also 25. Now you can see that this is 50 and this is 25. Also you have another clockwise moment where the value is unknown. So if you add these two beam moments, it should balance the column moment of 50. For definitely you will have MHI equal to 25 and MHI is equal to MIH is equal to 45. Now watch out here, it's quite interesting that at this point the column moments at the point D, there are two columns DG and DA and also only one beam DE. So this 25 is the column moment which is added with the column moment at the bottom 25. Why do we add this? Because both are in anti-clockwise direction and you end up with 45. This 45 is definitely balanced by the clockwise moment MDE. So MDE value should be 45. Once you find out MDE value is 45, MED is also 45. Now you can watch out here that 50 plus 40 is the column moment 90 and the beam moment is 45. So 90 minus 45, definitely this is 45. And here also this FE will be 45. You can cross check it with the column moments. 25 plus 20 is equal to 55. Yeah, this is how we estimate the beam moment. So it will be, it's represented here. At each and every joint, you can find out that the beam moments and column moments nullify the effect of each other. So by using that summation of moments acting at the joint is equal to 0, you can evaluate the moments of the beams from the column moments. Yeah, it has been shown how it is how the beam moments are balancing the column moments. You can see that the red color numerical written in the form of red color numbers and red color number represented by the numbers 25, 45. All these are representing the beam moment. Okay, so you can see that this 25, 25, 45, all these are the beam moments which have been evaluated from the column moments. Now shear in the beams, how to evaluate the shear in the beams? It's very simple as you calculated for the column moments. So 25 plus 25 divided by 4. So that is 12.5. So this is 12.5. Similarly, here 25 plus 25 is 12.25 plus 25 divided by 8 is 6.25. So that is represented here. Then 45 plus 45 divided by 4, here it is 22.5. Here 45 plus 45 divided by 2 divided by 8 is nothing but 11.5. So this is how we evaluate the shear in the beams. Proceeding further, so all the shears in the beams have been represented here. Already we have calculated the shear in the columns at the very first step. So what next? So we have evaluated the column moments, beam moments, and also we have evaluated the shear force in the columns, shear force in the beams. Everything has been evaluated. The next step is to calculate the axial forces in the beams as well as the columns. So this is the final representation of the free body diagram showing you the beam moments, column moments, shear in the column and shear in the beams. Now the next thing left out is the axial force. So in this diagram I have omitted the beam moments and column moments. You will find out the shear in the beams and shear in the columns, and also you will find out the axial forces. So here these forces represented in pink color represents the axial forces in beams as well as in the columns. Now you have to take each and every joint and apply the equilibrium conditions, summation of V equal to 0 and summation of H equal to 0. Once you use that methodology, you will be able to find out what is the axial force in the beam and what is the axial force in the column. So first we take joint G. So in this joint G, you can see that this is the axial force which is not known to us for the beam, and this axial force VV is not known to us for the column. We know only the beam shear and we know the column shear and the load acting at the joint G. So we have taken the joint G and the forces acting. You apply summation of V equal to 0, you get VV equal to 12.5. You apply summation of H equal to 0, you get VH is equal to 30, because this 30 and 10 are nullifying the 40. and VV equal to 12.5, because this vertical force 12.5 kilonewton is balanced by the opposite VV acting in the opposite direction by 12.5 kilonewton. So using the equilibrium equations, you can, I'm taking the joint, simply you can evaluate the shear in the axial force in the beams and columns. Similarly, you take the joint H, and this VH and VV are unknown. So you write down the equilibrium equations, you take all the forces acting towards right as positive, and the forces acting upwards as positive. You can follow any sign convention, does not make any difference at all, and ultimately we end up VV equal to minus 6.25. What does this mean? If you are getting a negative sign, it means that the assumption is wrong and you have to change the direction of VV like this. So VV is 6.25 in opposite direction, but actually we have assumed it to be acting upwards, but through the calculations we find out that VV should be acting towards down, that is downwards. Now VH is equal to 10 kilonewton. So VH is 10. You can see that this 10 plus 20 are balancing this 30 kilonewton acting in opposite direction. So this is the beauty of civil engineering, that how the forces nullify each other and balance each other. Now joint I is taken. Very simple, that here there is no VH or the, already you have calculated from the joint H, that is 10 kilonewton is the axial force in the beam. Now we have to calculate the axial force in the column. For that you apply summation of V equal to 0. From that you are getting VV equal to minus 6.25. It means that you have to apply the force in axial force in opposite direction, and the magnitude of the axial force is 6.25 kilonewton. Now joint D. Now you take joint D and apply the equilibrium equations. You get VV equal to 35 kilonewton and VH equal to 18 kilonewton. You can see that if you take VV, you have 12.5, you have 22.5, and it is balanced by this force VV. So these two are nullifying the effect of VV, ultimately yielding you VV equal to 35. Similarly, this 16, 10, 24 are going to balance this VH. So if you apply the sign convention and write down the equilibrium equation, that all the summation of all horizontal forces equal to 0, you end up with VH equal to 18 kilonewton. Similarly, joint E, here I have not changed the direction, but I have taken minus 6.25, which was calculated from the earlier calculations. So substituting all the values, you get here VV equal to minus 7.5 and VH equal to 6 kilonewton. Similarly, joint F, we have seen that we end up with minus 6 kilonewton, and here summation of V equal to 0, so 11.25, and VV is in acting upwards. So you can see that here 11.25 minus 6.25 minus VV equal to 0. So from this you get here VV equal to 17.5 kilonewton. Okay. Now these are the final calculations and the final free body diagram, where you have the axial forces, the shear forces in the beam, shear forces in the columns, and the horizontal reaction. This horizontal reaction is equal to 16 and HB equal to 32. HB here it should be HC equal to 16. Then RB will be equal to this axial force, RA will be equal to this axial force, and this is RC and this is MC. So this RC is equal to this 16, and MC will be equal to the moment at the joint D. There is anti-clockwise moment for the column MDA was found. Similarly, here you found anti-clockwise movement for MEB and for MC. So finally, we end up with the RA, HA and MA, RB, HB, MB, RC, HC, RC and MC. You have these values for RA, HA, MA, RB, HB, MB, RC, HC, MC. So this is how we solve the portal frame method using the principles of the point of contra-flexure as well as calculations of the joint using the equilibrium equations, and you using the basic concept that the interior column shares twice the shear as that of the exterior columns. Using that methodology we have solved, and also we have assumed the beam moments to be, that is beam moments to be clockwise and column moments to be anti-clockwise. So using this sign convention I have solved. If you want to change the sign convention you can change, but definitely you will end up with the same answer but negative sign. So this is how we solve the problem. If you have any doubts, you mention in the comment section. Thanks a lot for watching.